26, identify the type of hybrid orbitals in a specific molecule. Well, in addition to sp3 hybridization, there is sp2 hybridization, where the s and 2 of the 3 p orbitals blend together, but 1 p orbital is left as its own p orbital. And I showed you this demonstration in class, and we can have carbon atoms that have hybridized orbitals merge together, and a p orbital that is not hybridized just kind of bumps into another p orbital that is not hybridized. Okay? That's an sp2 hybridization. sp2 hybridization. In sp hybridization, an s and one of the p orbitals merges together, and the other 2 p orbitals stay as regular p orbitals. That's how triple bonds form. Take a look back at some of the transparency sheets that we have posted on Moodle, and some of the assignments that I gave you to work on in class for some better pictures of that. 27. Explain the relationship between dipole-dipole forces and London dispersion forces. Okay, dipole-dipole forces are weak forces. London dispersion forces are weak forces. Weak forces of attraction between molecules. It's one of the reasons why molecular compounds have lower melting and boiling points than ionically bonded compounds, because there's less of attraction between those subparticles. But a dipole-dipole force is when 2 polar things come near each other. And of the weak forces, that's a pretty strong one. London dispersion forces with those instantaneous dipoles or induced dipoles, those are very, very weak forces of attraction. Some great animations posted for you on Moodle. They're straight from your textbook, real quick, like less than a minute to watch them, that will show you that animated. The more polar the molecule is, the stronger the intermolecular attraction, with water in its hydrogen bonding being probably the most extreme example of that. But still, all of those nowhere near the strength of attraction in an ionic bond, in an ionic crystal. Okay? So know the kind of the order of from strongest to weakest of the weak forces. Test hit number 28. Explain how hydrogen bonding affects boiling point. Well, that goes back to what I was just saying about hydrogen bonding being the strongest of the weak intermolecular forces. And the more hydrogen bonding, the higher the boiling point. So the stronger the hydrogen bonding between particular molecules, say between water molecules or hydrogen sulfide molecules, the higher the boiling point of the substances. Excuse me. So you'd be comparing a couple different substances in this question. Question number 29. Identify a polar molecule from a list. Now, here's where you're going to need to know your geometries. I'm not going to give you any wildly weird examples here. These are going to be molecules that you have drawn and built and drawn Lewis structures of time and time and time again as we've been working through this chapter. But you should be at the point now where you can look at a molecular formula and recognize what that shape's going to be. If I say H2O, it should immediately come to mind that, oh, that's a bent molecule, water. If I say CH4, it should immediately come to mind, oh, 4 things attached, that's got to be tetrahedral. If I say CO2, probably some double bonds in there, that's going to be linear. If I say NH3, oh, nitrogen, 1 unshared pair, that's going to be a pyramidal molecule. Which of those is polar? Well, our methane molecule is not. It's very symmetrical. There's equal pulling power going on in every direction. Depending on which way we try to cut it in half or look at it, it always looks the same. The molecule overall is nonpolar. As opposed to something like CH2Cl2, where we have a chlorine end and a hydrogen end, that makes this tetrahedral molecule polar. Water, with its unshared pair of electrons, if we divided it in half this way, we'd have unshared pairs up here and shared pairs down here. That is a polar molecule. But carbon dioxide, where we have equal pull on each side of this molecule, that's a nonpolar molecule. We've been over this many, many times. I think once you see the examples, you'll have no trouble with that one. Brings us to test hint number 30, the last one. Explain how dipole interactions affect boiling point. Well, again, I'm going to ask you to compare a couple different substances. I'll give you the specific substances, and you should look at the kinds of bonding they would have. Are those polar molecules? Are they nonpolar molecules? If you have a sample of a substance that is all nonpolar, that might just have instantaneous or induced dipole attractions, the very weak London dispersion forces, as opposed to molecules, a sample of molecules that are polar, that are going to have dipole-dipole forces, or maybe even hydrogen bonding holding them together. Well, that second example with the dipole-dipole forces, that's going to have a higher boiling point than something that is just an induced dipole or an instantaneous dipole. And if those terms mean absolutely nothing to you and you're listening to this right now thinking, oh my gosh, what is she talking about? Then you need to get into your textbook and take a look at those basic definitions, and you need to go on and watch the animations that I have posted for you. And that takes us through the 30 questions in this part of the chapter. I've given you some hints about honors page material here, some of the calculations and things you're going to do. Remember, honors page is going to cover both the ionic and covalent part. You might want to flip back through the ionic test hint videos and listen to all the clues that I gave you in there so that you're prepared for your honors page. This one has some drawings, it has some calculations, it has a lot of just basic definitions, so it's not too bad, but you will be comparing and contrasting ionic bonding with covalent bonding. In fact, you should even be able to make me a list of here's what everything is about ionic bonding, and here's what everything else is about covalent bonding, and compare and contrast similarities and differences between the two types of bonding, well, and even metallic. Okay? Happy studying. Good luck on your test.